Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
So, what's today's episode on?
Oh, this is a good one, okay?
Okay.
Quantum computers.
Again, didn't we do that in episodes 5 and 8?
I didn't know, Baba.
And we've been throwing around this word too casually. What do we mean by the word quantum?
Okay. We'll address all of these problems and we'll explain the science behind quantum computers in this episode, okay? So, as we were saying, quantum exactly means the discrete amount of any physical quantity, such as momentum or electric charge. Okay, it's basically when we go really deep into the world of atoms at the smallest scale possible. So, like discrete, okay? And we try to quantify things and make measurements. That's what we mean by quantum.
And now if we say quantum computers, they're not even, by the way, at this point, they're not even science fiction.
Yeah.
We, as in the world's leading physicists like Edward Witten and all,
Huh.
are on the brink of a new technological era that's changing the rules of what's possible. And this is very significant, and of our time, this is probably one of the most significant developments, and it's probably life-changing.
Okay. Enough of philosophy. Let's get back to physics.
Yeah.
Huh.
So a classical computer performs operations using classical bits.
Correct.
Simple as that. And these classical bits can be either 0 or 1.
Huh.
In contrast, a quantum computer uses quantum bits or qubits. QUBITS. And they can be both 0 and 1 at the same time. This is what quantum superposition.
Correct.
Or Schrodinger's cat, episode 5.
Huh.
So this is what gives a quantum computer its so-called superior computing power.
Yeah. And I've read that there are a number of physical objects that can be used as a qubit. So like a single photon, a nucleus, or even an electron. And nowadays, researchers have started using the outermost electron and the phosphorus atom as a qubit also.
This phosphorus is being used a lot these days.
Yeah.
Even in transistors last episode, and abhi quantum computers maybe. Wow.
But how does that work?
Well, all electrons have magnetic fields.
Huh.
So they're basically tiny bar magnets, and this property is called spin. If you place them in a magnetic field, they will align with that field just like a compass needle lines up with the Earth's magnetic field, right?
Huh.
So same like that. It's like that.
Yeah, and this is the lowest energy state. So you can call it like a zero state, or for the electron, we can call it spin down. Now, you can put it in a one state or spin up, but that of course takes some energy, right?
Yeah, so if you have your compass and you just break off the glass because you won't be able to touch the needle otherwise, but if you break off the glass and turn the needle the other way, you'd have to apply some force to it, right?
Yeah, you have to push it to flip it to the other side.
Yeah.
And this is what we call the highest energy state. And in principle, if you were so delicate to really put it against the magnetic field.
Exactly.
Exactly. Okay. 180.0 degrees.
000, significant figure.
Okay, yeah. Precision.
Yeah, accuracy.
It would exactly stay there.
So basically, so far, we've just been talking about classical bits. This is just a classical bit, right? It's got two states, spin up and spin down, which is 0 and 1. But the funny thing about quantum objects is that they can be in both states at once.
Correct.
And when you measure it, the point with quantum is, when you measure it won't be like a superposition. When you measure it, the wave function collapses and you measure only either spin up or spin down. Only either one of them.
But the catch is that this is the interesting part, okay?
Yeah.
Before you measure it, the electron can exist in what is called a quantum superposition. And where these coefficients basically spin up or spin down, they indicate the relative probability of finding the electron in one state or the other. So basically, before making a measurement, it can exist in any state. That's why we say that it exists in a superposition of states.
Yeah. And it's little hard to imagine how this enables this incredible so-called computing power of quantum computers without considering two interacting qubits, right? So there are 4 possible states of 2 interacting qubits. Let's just assume electrons. So let's say there are 2 this is, you might think that it's just like 2 bits of a classical computer. So, like, let's just search a classical computer will have 2 bits, which are going to be 4 possible scenarios.
Correct.
0, 0, 0, 1, 1, 0, and 1, 1. They're 4 numbers, but still 2 bits of information, right?
Yeah. And all I need to say to determine which one of these 4 numbers you will have in your computer code is the value of the first bit and the value of the second bit, right?
Yeah.
But instead, in quantum mechanics, you're allowed to make a superposition of each one of those 4 states.
So we can write a quantum mechanical state that works perfectly and is legitimate. That is a sum coefficient times each of the possibilities. Like there will be 4 coefficients.
Huh.
So to determine the state of this 2-spin system for quantum qubits
Correct.
or electrons which we took, we need to use 4 numbers of 4 coefficients. Alternatively, in the classical example of 2 bits, we only needed 2 bits or 2 numbers.
Correct.
This is how you understand why 2 qubits actually consist of 4 bits of information.
So we need 4 numbers to describe the state of the system, whereas for a normal or classical computer, we only need 2 of them.
Yeah, literally.
And now if we make 3 spins, we would have 8 different states, and it could give you 8 different numbers to define the state of those 3 spins. Whereas in classical computers, it would just be 3 bits.
Yeah, 3 bits, 3 spins, literally.
Huh.
So if you keep going, like from 3 to 4 classical bits, you find that the amount of equivalent classical information contained by n qubits is 2 to the power of n classical bits, or basically 2 raised to n.
Huh.
So, of course, the power of exponentials, like, they're very, as you grow, they grow, like, way more, right? Exponential.
Of course.
So, once you have, let's say, 10,000 qubits, in what's called the Foliant angle state, where you have to create these really crazy states, and there's a superposition of all 3 angles being a specific way for 2 to the 10,000 classical qubits, which is like 99,700 times as many particles as there are in the universe.
Okay. Those are too many numbers to digest, okay? I'll just tell you this.
Yeah.
There is a catch, okay? Although the qubits can exist in any combination of states, when they are measured, they must fall into one of the basic states, which is up or down. And all of the other information about the state before the measurement is lost, okay? So you don't want generally to have as the final, you don't want the final result of your quantum computation as something which is a very complicated superpositional state.
Yeah.
Because you cannot measure a superposition. You can only measure one of the basic states of the electron.
Yeah, like down, down, or up, or down, up, or up, down. One of the 4 possible.
Yeah. So not confusing.
Yeah. So what you want to design is the logical operations that you need to get the final computational result in such a way the final result is something you are able to like measure, right?
Yeah.
Just like a
Quantify.
unique state. Yeah.
Correct,
Quantify.
correct.
Yeah.
And it is this kind of reason why quantum computers are not a replacement of classical computers. It is not that they are universally faster.
Yeah, because they're only faster for some special types of calculations where you can use them, use their advantage, right? You can use the fact that you have these quantum superpositions available to you at the same time to do some kind of computational parallelism.
Yeah, if you want to watch a video in high definition or
MKBHD.
Yeah. Or browse the internet or just like do some documentation, they're not going to give you any particular improvement if you need to use a classical algorithm to get the result, right?
Yeah, so you should not think of a quantum computer as like something is going to be like a daily driver of what like day-to-day people, like normal people. But it's not something where every operation is faster. In fact, it's probably going to be like slower in the computer you have right now. Except your computer, Pratham.
Yeah, don't make so much fun of it.
But it's a computer where the number of operations required to the result, like to arrive at the result, is going to be exponentially smaller because it makes certain calculations for it as fast as Usain Bolt at the 2009 World Championships.
9.58 seconds.
Yep.
Absolute legend.
Yes, I agree.
Arnav's dream, but like, he's too slow for that.
Fine, I agree, but only for now.
Yeah, you almost like made us lose a relay once, okay? But that's a story for another day. We'll take that up in an exposition Q&A.
Yeah, by the way, we just came first, huh? We did come first in the end.
Yeah.
Okay, so there's still one big hurdle in making quantum computers mainstream. Quantum error correction. See, Qubits are incredibly delicate because they're prone to interacting with their surroundings. This is called decoherence. We've done that in high energy.
Yeah. Correct.
So this interaction, like the high energy cosmic rays with the surrounding space, this can introduce errors into the system. And since they're in superposition, the qubits, even small disturbances can change their state. And this can like just yeet the entire calculation.
Yeah, and now classical computers already deal with errors using error correction techniques, right?
Yeah.
But the challenge for quantum computers is like much, much bigger. We can't just copy a qubit state.
Control C, Control V.
Arey haan re. We can't just copy its state like we do with classical bits, but
Why?
I'm coming to that. Wait.
Yeah.
Curb your enthusiasm, okay?
Sure.
So, well, in the quantum world, copying is basically a no-go because of something called the no-cloning theorem. You can't clone a quantum state perfectly. You can't even measure a quantum state perfectly, right? So, how do we correct these errors?
So scientists like Edward Witten have come up with clever methods to overcome this. Instead of copying the qubit, this quantum error connection involves like us spreading information across multiple qubits. So like usual technique that scientists use right now is to encode a single logical qubit into multiple physical qubits. So like electrons, the other physical qubits. That way, even if one qubit gets disturbed or lost, the overall quantum information can still be recovered, kind of like a MongoDB database.
But the big problem arises is...
Again,
yeah, this requires a lot of qubits. I mean, a lot of them, okay?
10 to like 2 to the power of 10,000?
No, not that much. But for every single logical qubit, you might need like dozens or even hundreds of physical qubits just to maintain that error-free quantum state. And this makes scaling up quantum computers a massive challenge.
Fair.
Even the largest quantum computers to this date have like 100 to 300 qubits. And most of these are dedicated to error correction and not actual computation.
So they're like not even doing actual stuff till now. But like they have a good possibility.
But potential is the key word over here. Yeah.
So this finally brings us to a really important point: quantum supremacy. You may have heard this term before, but basically it's a point where a quantum computer can perform a task that no classical computer, even the most powerful supercomputers, can accomplish in a reasonable time. The real value of quantum computers lies in solving practical problems that are currently just beyond the reach of classical computers. Like, for example, stimulating molecules for drug recovery. Arey, not that type of drugs, yeah.
Arey yaar.
Medicines. So, like, think about stimulating models for drug recovery, optimizing complex financial models, like the $1 trillion equation stocks and all, or even cracking modern cryptographic systems.
Financial mathematics major.
Yeah. These are just some areas where quantum computers could be revolutionary, but we're still slightly a few breakthroughs away from seeing them applied at this scale.
Yeah. So while quantum computers hold incredible promise, we're still in the early stages of their development, right?
Yeah. Potential.
Potential. So it's a bit like the early days of classical computers.
Yeah.
Remember when they were like taking up entire rooms and their like potential applications were still in discovery.
Yeah.
But with the pace of the research today, kya pata?
Yeah, like Moore's law can still be applicable to this as well, like getting faster every time.
Arey kya pata yaar, 2 saal mein we'll have quantum computers doing everything now.
ChatGPT, but quantum
GPT. Jinx.
So the improvement is not in the speed of the individual operation. It's in like the total number of operations you need to arrive at the result, as we said earlier, right?
But the only case, that is only the case in particular types of calculation, like particular algorithms. It is not universal, which is why a quantum computer is not the replacement of a classical computer, but nonetheless, it still holds the potential to be something extremely, extremely great.
So you won't be seeing any classical computers being replaced by quantum computers anytime soon.
Yeah. So potential employees, don't be fazed by this. You're going to keep your jobs, okay? Chill out.
Chill.